Hello, everyone. My name is Justin Ting, and I'm from Georgia Tech's Integrated Circuits and Systems Research Lab. And today I'll be talking about how we combine event-based vision and spiking neural networks to create a system that performs gait imitation. Before I go into exactly how we do that, it is important to understand some of the background and motivation behind why we do this. So, computer vision and deep reinforcement learning, we know that these algorithms are very wonderful and they do many powerful tasks, but they are also very power hungry and require vast amounts of data, which in robotics, that's very hard to obtain. When we look over to how humans and animals work, though, we can see that they compute their motion problems of equal complexity and in orders of magnitude more efficiently, meaning they can perform with far less data and electrically more efficiently. So this is why we want to take a look into brain-inspired technologies and understand the relationship between perception, computation, and actuation to understand how we can take the system and make robots that don't need a lot of data to move, to do intelligent movement, and don't need a lot of electrical power to be able to pull off these algorithms. So the imitation learning approach, what does imitation learning mean? In the past, it's simply a problem where if you think about it, you can, if you go on YouTube and type in how to do jumping jacks or how to do a certain dance move, you can watch the video and watch the instructor do the move. And without any explicit instruction, you can kind of figure it out how to do it for yourself. And imitation learning is a very biological process that can be observed in many mammals and in humans. So instead of giving robots explicit data to work off of or specific action spaces, we hope, in this case, we want to be able to show a robot a video of someone walking. And in this case, the robot just looks at that and is able to go, okay, I know how to do this. I know how to move the limbs and how to actuate so that I can copy whatever I am seeing. And to be clear, the paper does not use the imitation learning techniques that have been used in the past, which involve a lot of reinforcement learning or a lot of policy estimation. We take on a much more bio-inspired approach to imitation learning. So we are looking for something bio-inspired, which means we want our agents to be able to process this data as it's learning. So while it's watching a video of another robot moving, it's twitching its legs, trying to copy that movement, and it's thinking and processing at the same time as it's doing it. So the data takes a form of a sparse stream, right? We want this to be a temporal kind of algorithm, and we want it to be dynamic. On the right here, first of all, we use RAS clause, a deep RAS clause, which is a hexapod that's run by Raspberry Pi. It's pretty commercially available. And you can see an overview of our flow here, which it goes at the top, you can see the vision side, and then it goes through a filter, and through that filter, it goes to the spiking neural network, and then it goes on to the spiking neural network into actually actuating the robot. So we will go more into this later. The two brain-inspired technologies that I want to briefly touch on are event-based vision and spiking neural networks. So in order to understand event-based vision, it becomes very clear once you actually just look at what it does. So on the left here, we have very normal footage filmed on an iPhone of our robot just moving its legs. And on the right side, this is how event-based vision looks to us. You can see it's just bright and dim pixels all over the place. And when movement occurs, more pixels light up. So this is the type of camera that only detects movement. So why are we interested in event-based vision? Well, first of all, in terms of the specs, event-based vision triumphs over frame-based cameras in many aspects, such as the latency, such as dynamic range, and far less power consumption in the milliwatt range. It saves this much power because each of the pixels are independently and asynchronously sampled, whereas for frame-based cameras, all the pixels are sampled at once, which means that you will inevitably sample some pixels. You'll spend some electric power sampling pixels that are not relevant. So because every single pixel is able to sample independently, it's able to sample a lot faster, and this results in no motion blur. So much more data about motion can be captured with far less storage, far less megabytes. So this state space, this output of event-based vision, is the stream of pixel events, the stream of ones and zeros. If it's a 1, that means there's a lot of movement in such a location. And if it's a 0, it means that not much movement is happening and therefore it's not relevant. The second brain-inspired technology to touch on is spiky neural networks. It's a computational model that mimics biological neural networks, and it works dynamically. So these models have been used to perform simple image recognition on MNIST and also language processing. How it works, though, is that every neuron is governed by a set of dynamic equations, which are shown, the ones that we use are shown on the bottom left. And these equations determine the way that the voltage behaves. So on the right side, in the red graph, you see it's keeping track of the voltage in a single neuron. And this voltage goes up whenever it receives more inputs, and then it rests. It goes to a resting position if it does not see inputs. And the inputs are spikes, which are, you can think of them as Kronecker deltas, and they are either a 1 or a 0 at a particular time. So it's just a flow of spikes here. It's either on or off. And the voltage it goes higher. The voltage inside the neuron goes higher when the input spikes are much more condensed, or the weights on those spikes are very high. And when the voltage goes above a certain threshold, it will output a spike itself. So it inputs spikes and it outputs spikes. And through this process, it's able to encode information temporally. It's able to keep track of the distances between the spikes, the number of seconds between them, and use that information to make a judgment on whether I should do an output spike or whether I should not. So the algorithm itself, first, I want to touch on the filter, the event-based filter. Here we only use min pools and max pools. And the event-based vision, like I mentioned earlier, is all binary. It's a binary stream. So that means it only consists of 1s and 0s. And when you have just 1s and 0s, your min pools and max pools become OR pools and pools. And I use them both here. So the reason why I use this change in terminology is because I want to change the mindset, the perspective we want to be here is not just using PyTorch or TensorFlow to throw a max pool on this. We are looking at the potential for doing a purely digital filter that will save energy. So the demonstration of what the filter can do for event-based vision can be demonstrated by just watching what it does. Here we have another iPhone recorded robot that's just moving its legs. Here, I want you to pay attention here. This is the event-based footage. You can see a lot of noise around the robot. You can see that there's pixels lighting up when there's not much moving there. So here is the filtered version. When it's filtered, you can see that the noise disappears. And the only place you can see pixels is on the robot. So you only see the robot, which is the only relevant information in the footage, and this is what you get. Now here, the body of the robot disappears, and you only see the legs moving. It's kind of difficult to see, but if you see a spark of pixels, that is indicating that a leg is moving in this location. So this narrows down the amount of relevant information even more, where you only see the legs and you don't even see the body of the robot. You only see the part of the image that's moving the most. So the weight adjustment algorithm, so spiky neural networks and event-based vision connects well together because event-based data is a flow of binary information. It's a flow of spikes, it's a flow of 1s and 0s, which are the same thing. Spiky neural networks take in spikes and output spikes. So there's this very intuitive connection between the two brain-inspired technologies that make it easy to manipulate. So our spiky neural network consists of one layer with 6 neurons, and each neuron controls a single leg. So whenever a neuron outputs spikes, it's telling that leg to move. So in its essence, this spiky neural network becomes a central pattern generator where it's outputting a sequence of spikes, and the sequence of spikes is telling the robot which leg to move at what certain time. The flow from the pixel all the way to the leg looks a little like this. To really simplify what this is saying here, this is pretty much saying that if a neuron sees a pixel and it activates, that means that this pixel at this location is important. So all the neurons are fully connected to all the pixels in the event-based camera. And the weights go up if it sees a pixel activating very frequently. And if it sees a pixel that doesn't have a lot of activity, the weight starts sinking with time. So every milliseconds, this weight is slightly decreasing. But the weight increases quite a lot when it sees a pixel because it recognizes that as important information. And when you have a higher weight on the neuron thinks, okay, I have to start sending spikes to the leg so that the leg will move. I want to start telling this leg to move because it's seeing a lot of pixel activity in this particular regions, which means that I want this, which means that this leg should be moving. So the Gaussian leg estimator touches on the problem where, you can see pixels activating, but you don't know where you should activate them because there are 6 legs. How do I know which leg to activate? How do I know which neuron to pick to spike? The problem with this is that leg labels have a non-unique solution, meaning that I can have labels 1 through 6 for these legs, and this label 1 can go anywhere. It doesn't really matter. There's no way you can really model what leg should be what number. So we have to put some priors. We have to lay the priors on top so that how we determine it is if you use OR pools, you can find the centroid of the robot very easily. You can find the center of the body, and you can find the place where the leg spiked. And if you find this angle, this arbitrary angle between these 2 points, then you will be able to find the probability that's a certain leg. So in this example in figure A, you get a theta from the leg that spiked, and using that theta in figure B, you can use these probability distributions to say that there's a very high probability that this particular spike corresponds to leg 6. And using this very unsupervised model-free estimation of legs, we're able to get the signals in the right place. So the results, first I want to focus and demonstrate the convergence where in figure A right here on the upper left, you can see that in the first 100 seconds, the voltage is unsure, where it's oscillating slowly and it's seeing the pixels, but it's like, I'm not sure if I should be moving this leg yet. But as time goes on, it's more and more sure that I should be moving this leg. So if you look at figure C, you will see a raster plot. A raster plot pretty much puts a dot at every time there's a spike. And on the y-axis, you see the legs. So and on the x-axis, you see time. So at a certain time, if there's a dot, that means that leg moved at this certain time. And during training, you can see in the first 50 seconds, the robot is not really getting the hang of it, but around 100 seconds, it starts picking up the gait that it's seeing. So it takes some time for it to converge, but it only takes about around 100 seconds. So in figures B and D, you will see similar things, except here in B, leg 2, the voltage is spiking all the time. And that's because it's already trained. So we give it a different gate, and then the voltage already knows when to spike. So in figure D, you see the raster plot of this new gate, and it's alternating legs 1, 3, 5, and then 2, 4, 6 back and forth periodically. So if we show a new gate to the robot, then it will be able to imitate that more easily because it already got trained on the previous gate in part C. So this is how the voltages in figures A and B correspond to the gates, the walking gates that you see in figures C and D. So here's a video that demonstrates how the student and the expert syncs up. The student is watching the expert, and right now the student is syncing up with the expert. So at the beginning of the video, the student was not synced up, but now now they're in sync. So this is a demonstration of what it looks like when a student catches on to what the expert is doing. So in terms of energy estimations, we calculated about 1 microwatt for the whole system because the filter takes about 2 to 3 nanowatts based on typical digital systems, and the spiking neural network, if we base it on Loihi processor specs, it takes about 5 nanojoules per cycle, which means that this technology has a lot of potential to be in very power-constrained scenarios like micro-robots with the simple algorithm of boosting weights and decreasing weights. So right now, I am open to questions, and I look forward to hearing them.